Okay. So, and I don't know, some people might be also online. I have no idea what's happening. Okay. We're doing on time. You should say hi, Richard. All right. Oh, did you see Richard? And I want it to be so you can see. I think everyone is. Here's Martha's coming in. All right. So I think I will start. So I want to welcome everybody back to the seminar. So we have a special treat today. So Galen Dorpalen-Barry is speaking today on the Poincaré-extended AB index. And could you please pronounce your university? Because is it Ruhr-Universität Bochum?
Yeah, that's super. Ruhr-Universität Bochum.
So it's just like
in Germany. Sorry?
It's just like Swedish. Ruhr-Universität Bochum. Sama. Okay, perfect. Now I'm going to speak. Okay, take it away. Thank
you so much. Thank you for inviting me. I'm really excited to be telling you about this project that I've been working on recently with my colleagues, Josh and Christian. Both of them are here in Zoom. And we're sort of excited to show what we've been doing. I divided this talk into 4 pieces. So first, I'm going to give a big picture overview of the object we're studying and the reason that we wanted to study it. One thing that's that I'm going to do a little bit out of order is I'm going to first explain the object and then motivate it. In the second part, I'm going to talk a little bit about the techniques that we use to solve the conjecture we want to solve. So this has to do with R-labeled posets and generalized descent sets. In the third part, I'm actually going to talk to you about like the main theorem and well, the coefficients of this extended AB index. And finally, I'm going to talk about some of the connections to the ordinary, the non-extended AB index. So the first part of this talk is the big picture. And as I said, I'm going to first define the objects, and then I'm going to try and motivate them to you. So let's just start with some definitions for posets. I'm going to be thinking for the most part about posets that have a 0 hat and a 1 hat, meaning they always have a unique minimum element and a unique maximum element. So there's 3 posets on the side of the screen. Oh, they're not quite all visible. Let's see. Aha.
Ah, great. Thank you.
So this first one here, there is a unique minimum element, but not a unique maximum element. There's these like 3 pieces at the top here. And the other 2, well, we'll get into those in a minute, but they have a unique minimum and maximum. So for me, a chain is going to be a subset of the vertices, or some of these dots. And I'm going to say it's maximal if all of the successive elements are related by cover relations. Thirdly, I'm going to say it's graded if all the maximal chains have the same length. And I'm going to say it's graded of length n if all of those maximal chains have length n plus 1. A lot of what I'm going to do has to do with intervals. So these are, I fix 2 elements that are related in the poset and all elements that are in between them. Give me 1 minute. I'm going to pause for a second. Oops, does that work? Something. Okay, give me 1 second. You got a technical issue?
Nothing ever works as soon as you start. Just a given.
Yes, of course. And the moment it's recorded. Okay, great. So
then we're real people.
Yes.
Perfect.
So one of the core objects or one of the things we're going to need in this is the Mobius function of a poset. We've probably all seen this before, but it's defined recursively where the Mobius function, if you start at the bottom element, so the 1, 1 element or the 0, 0 element, it's always 1. And then if you go up to an element, what you do is look at all your Mobius function values below and sum them up and then flip the sign. So I think I don't have an example on this slide, but maybe you can see my mouse. Can you see my mouse if I move it around? Okay, great. So the Mobius function of this Boolean lattice here, we start with a 1. If we want to know what the Mobius function is on the interval of these 4 elements, we say, okay, this is a +1. The interval here, we get a -1 because we look below. And then this one is also a -1. So then on the whole interval, it's -1, -1, +1. And then I flip the sign to get a +1. And then if I play the same game again on maybe this whole interval in this poset here, I get a +2 on the top of the whole interval. Because it's graded, I can define a rank function recursively. So I start with this unique bottom element being the 0, and then as I go up, I just add 1 to my rank values. And I use this Mobius function and rank to define the Poincaré polynomial of the poset. So what I have here is this definition is the Poincaré polynomial of the poset. It's the sum of the absolute values of the Mobius functions, and I keep track of how high I am in the poset using y to the rank of x. On the right-hand side, I have these two posets we've been looking at and their Poincaré polynomials. So the top one, I have one unique bottom element of rank 0, and so that's a 1. The first thing in my Poincaré polynomial is always this unique bottom element, and always gets a 1 times y to the 0. And then this in first rank, I have 3 elements. Their Mobius functions are -1, -1, -1. I take the absolute values, and so I have 3 times 1. And then I have the same thing in the next row, and then finally y cubed. The second example is this smaller poset, and it's sort of more interesting because that big interval has a +2 to the Mobius function. So I have 1 on the bottom element, -1, -1, -1, which gives me my 3, and then my +2 at the top. And this polynomial has connections to the geometry of hyperplane arrangements. It's a specialization of the top polynomial under certain circumstances. And it's something that's very well studied in mathematics, especially in sort of my field, which is a lot of hyperplane arrangement and matroid stuff. In order to define the main protagonist of this talk, I want to introduce a weight function, which is a little bit different than this Poincaré polynomial. Oh, shoot, I'm out of order. I got ahead of myself. I'm not defining the weight function yet. Sorry about that. I'm first going to define the chain Poincaré polynomial. This is just when I have a chain in my poset, I have a bunch of littler graded posets in between those chains. So this is probably not a maximal chain in my poset. And I just define the chain Poincaré polynomial to be the product of all those little Poincaré polynomials. So here in my poset on the left, I have a chain of length 2. So this 2-element chain, so these 2 pink dots. And my chain Poincaré polynomial, I take the interval from this pink dot to this pink dot, and I multiply it with this pink dot to, I just go up to the top of the poset. So in this case, it's 1 plus y squared, because it's the Poincaré polynomial of the first interval times the Poincaré polynomial of the second interval. Let's do a slightly more robust example. Here we have this chain, which goes just this unique bottom element, and then this thing of rank 2 here. And you can see that what's happening in this little square is a more interesting Poincaré polynomial than the previous chain, which was just that little, I don't know, one element segment. So here in this 4-element piece, my Poincaré polynomial is 1 plus 2y plus y squared. And then when I go up to the top, it's a 1 plus y again. And so my chain Poincaré polynomial is the product of those the product of the Poincaré polynomials on those intervals. It's 1 plus 2y plus y squared times 1 plus y. Okay, now I'm going to look ahead on my slides. Okay, now I think we're really ready to define the weight. Before I do that, any questions about these chain Poincaré polynomials? Okay, great. So the weight of a chain is just a way for me to keep track of which ranks I've used when I've created my chain. It's not always totally clear from the Poincaré polynomial data what ranks that I chose maybe. So I want to keep track with a pair of non-commuting variables, A and B, which ranks I'm using. And how I do this is I define the weight of a chain to be a product, W1 through Wn, if n is the number of elements in my poset, not my poset, in my number of ranks. So Wi is B if the preceding, so Wi, it starts with a 1. So I want like the thing of the next lower rank is in my, something is in my chain of the previous rank. What I mean is in this picture here, I have nothing of rank 0 in my chain, so I wouldn't put a B in the first position. Instead, I put this A minus B in the first position. So here I have it on the side, the A minus B goes in the first position because there's nothing of rank 0. And then for the rest of this chain, I have something of rank 1, and that it corresponds to my B here, which is in the second position. And then I have something of rank 2, which corresponds to a B in the third position. Let me do another example just so you can see how this game works. Here again, I have a chain that has a 0 and something of rank 0 and something of rank 2. So it's a B, A minus B, B. And now we're ready to define the Poincaré-extended AB index. So I just take these chain Poincaré polynomials that I got as products of Poincaré polynomials as I go up a chain, paired with the weight. And now I've written it as a polynomial in A and B, but just to emphasize in this particular definition that I have something that's like a polynomial in Y, which is it's like it commutes with itself, but then I have these weight polynomials in non-commuting variables A and B. And I sum this thing over all chains of P where I remove that 1 hat element. So I just want to do a quick example and then maybe talk a little bit about what we might hope from this polynomial. So here on the side, I have a picture of a post that we've looked at a couple of times. Now I've labeled the vertices with 0 hat, 1 hat, and alpha 1, alpha 2, and alpha 3. That's just so I can keep track a little bit of what's happening with these maximal chains, or with these chains that I'm going to write down. So here in this chart, I have the first column is the set of chains of my post set. Not all of them are maximal. Actually, none of them are in the full post set because they don't contain the top element. But they're all chains of this P minus 1 hat. And then I've written down the Poincaré polynomials of these chains. So it's products of Poincaré polynomials. And then I've written down the ranks that these chains go through and all their weights. So let's just go through row by row what I mean. This first row is the empty chain, and I formally say it corresponds to the 1 Poincaré polynomial. And there are no ranks of that chain, so I have A minus B times A minus B. And that corresponds to this first entry, or this first term of the extended AB index down here. The next chain is this 0 hat. So the only interval, it goes from 0 hat all the way up to 1 hat, and it corresponds to the Poincaré polynomial 1 plus 3y plus 2y squared. And there's only one rank in this chain, it's 0. So my weight is B, A minus B. Okay, I'll go through a little more quickly with these next 6 chains. Here we have alpha I, so there's 3 copies of alpha I. Each of them corresponds to a chain that has something of rank 1 and then nothing else. So I get a 1 plus y 3 times. And this is rank 1. So the weight of each of those is A minus BB, which corresponds to this term here. And I do the same thing with the 0 hat alpha I chains, but now I get a 1 plus y squared because I have 2 things in the chain, and these correspond to the B squared terms. Which should be here. And if I multiply that out and I simplify, I get the following polynomial, which is A squared plus 3y plus 2y squared BA plus 2 plus 3y AB plus y squared B. So we can see that there's lots of cancellation, and something kind of surprising happens, which is that all those minus signs go away. It's not obvious that they go away. This is going to be a big part of this talk, is explaining why these coefficients are not negative. I want to give you one more example, and I just want to say I did not compute this example by hand. This is a bigger post set, and I made my computer do it. But here you can see again that the coefficients are non-negative. And the reason I'm making a big point about this is that there was a conjecture from Maglione-Voll that the intersection poset of an arrangement. So when you have an intersection poset of an arrangement of hyperplanes, I haven't defined that for you, but they do a little tweak to the extended AB index and they specialize the variables to 1 and t. So the A and B, they specialize. And they conjecture that this special case has non-negative coefficients. And what I want to prove for you in this talk, or convince you of in this talk, is that their conjecture is not only true, but it's true for a much larger family of posets than they originally conjectured. So I'm going to convince you that whenever P is a R-labeled poset, I haven't defined that yet, but when P is R-labeled, then the coefficients of the extended AB index are non-negative. Before we actually get into the proof, I want to first give you a little bit of motivation about why they would conjecture this. I'm going to pause here and take a sip of water. Are there questions? Okay, great. Give me a second.
Oh, we have cookies, by the way. Oh, cookies. We're taking a mini break.
Ha, great.
Sorry, we have cookies.
You should enjoy those cookies.
They're French, actually. It's like
French.
French. Ooh, that's chocolate.
I'm jealous. But
Sorry.
I'll keep talking. No, it's okay. I'm going to tell you a little bit about the motivation for these extended AB indexes and specifically the conjecture of Maglione-Voll. So when you have a central hyperplane arrangement in a real vector space, from that you can define an intersection lattice. So their conjecture is for all hyperplane arrangements. And if you are a hyperplane expert, you might realize that I'm specializing to central hyperplane arrangements where all the hyperplanes go through the origin. It's easy to extend the result to the affine case, and we can definitely talk about it at the end, but ask me about that at the end because it gets a little bit away from the main thrust of the talk. So Maglione-Voll prove, so they start with some kind of integral and they call this thing an analytic zeta function. They then do a monomial transformation on this and they get something which they call a flag Hilbert-Poincaré polynomial. And then they do a natural specialization where they set a bunch of variables equal to each other and they get something that I'm going to call the coarse analytic zeta function. And it has the form that I'm presenting here. Z sub A, because it's for an arrangement, and they look at chains of the intersection poset, and then this chain Poincaré polynomial where you force 0 to be in all of your chains. And they have this T over 1 minus T to the number of elements in your chain. I want to emphasize, this is a bivariate version of something slightly more general, which they call the flag Hilbert-Poincaré polynomial. And while the specialization they use to get the one that I've shown you is like a very natural specialization, there's a slightly less natural specialization that gives you the motivic zeta function of a matroid, which was defined recently by Jensen, Cutler, and Usatane. So you can think of it as there's one meta object and there's a specialization that made sense for Maglione-Voll, and then there's another one that makes more sense for these guys, Jensen, Cutler, and Usatane. And so this is not quite our extended AB index yet, nor is it the thing that I wanted to tell you about, this numerator polynomial that I want to show you. So I have to tell you a little bit more, which is that when you have this analytic zeta function, you can then of course put these all over the same denominator. So you put all these 1 minus t's together. This is kind of a harmless statement. And it's the numerator that Maglione-Voll were looking at. And so they conjecture that the numerator of this polynomial has non-negative coefficients. And the extended AB index is just that numerator polynomial, but instead of looking at 1s and t's, we look at this weight function with a's and b's. Okay. So just to summarize that in a slide, the numerator of this rational function is the sum over chains of these chain Poincaré polynomials, and I have t times 1 minus t, where I'm taking like things that are in my chain or things that are not in my chain, and I just keep track of that information. And so their conjecture says these numerators have non-negative coefficients. And I will add that there's a second specialization. So further specializing these numerator polynomials, those polynomials were also studied. So Kühne and Maglione studied the specialization of these polynomials at y equals 1, and they made a conjecture on the bounds on these coefficients. So this is going to come up because the y equals 1 case will show up a little bit later in the talk as well. It's something that other people have looked at for the extended AB index. But it's kind of interesting that sort of Kühne and Maglione were working with this y equals 1 case in a separate setting. And our proof that we're going to talk to you about today gives a proof of this lower bound almost for free. So now that's all I wanted to say about motivation. I now want to change directions and talk a little bit about the setup that we needed to prove their conjecture. So they conjecture that the numerator polynomial has non-negative coefficients. We're going to prove that these extended AB indexes have non-negative coefficients. I'm going to do this using R-labeled posets and a little bit of work with descent sets. So let's remind ourselves what an R-labeling is. If P is a graded poset, then I take E of P to be the set of edges of the Hasse diagram, i.e. the set of cover relations. And I say that a labeling of these cover relations is an R-labeling if every interval, so I label it with integers, and I say that every interval has a unique increasing maximal chain. So it's kind of technical and wordy, but let me show you on the example. Here on this left side, I have a poset that we've seen this a couple of times, and I've added purple labels to the edges. And you can see on this maximal interval, so from the 0 hat to 1 hat, there's a unique increasing chain, and it's this 1, 2, 3. If we go up a different chain, like this 2, 3, 1, it might increase or decrease. Or in this case, it might only decrease. 3, 2, 1. It's kind of hard to see, some of the labels get jumbled, so we can also see it on this poset. Here I've labeled the edges in purple, and the unique increasing chain is this one here, and the other two chains strictly decrease. I'm going to say that so when I have all these chains that are weak, when I have all these labelings on, when I have these labelings on all these edges, I can talk about descent sets and chains. So if I have a fixed maximal chain, I say that it has a descent at position I if when I go from the edge below I to the edge above I, the labelings decrease. So in this maximal chain, the edge labelings are 2, 1, 3. And from 2 to 1, the labeling decreases. From 1 to 3, the labeling increases. So this chain has a descent at position 1. Let's do another example. Here's another maximal chain. This has descents at positions 1 and 2 because, so here's position 1, 3 to 2, that's decreasing. And here's like the thing of rank 2, 2 to 1, that's also decreasing. And I want to generalize these descent sets a little bit by adding in a little twist, by adding in a subset of the edge. I want to shade a subset of the edges. Here's how this works. I start with a maximal chain and a subset of the edges of this maximal chain. And then I'm going to talk about a generalized descent or an ME descent. And so I say that I pick up a descent if one of the following 3 things happens. So first of all, if I have anything where the edge below my vertex is not shaded and the edge above is shaded, I pick up a descent. So this is my position I, and I go from not in E to in E, I pick up a descent. Or if my labeling is increasing, that's what I'm doing. I'm denoting with this little plus that this is smaller than, the labeling on this edge is smaller than the labeling on this edge, and both the edge and the edge below and the edge above are shaded, Then I also pick up a descent. And finally, if I just have a usual descent, so the edge below, the edge above are not shaded, and I'm decreasing over this edge, then I also pick up a descent. So you can think a little bit of like these edges. So in these two cases, where it's both in or both out, you can think a little bit of this labeling as reversing or like taking the minus sign. Actually, you can sort of think of it.
Yeah, but
Sorry?
The things in the set E to the put as a positive signs, and the things outside the set E should be when putting a negative sign in front of it.
Yes.
Okay.
I think you're already guessing where this story is going. I'm very excited. So we're not going to talk too much about that, but that's in principle what's happening. I'm going to do one sneaky thing where I'm now allowed to include 0 in my descent set, but only in this first case. So if that first edge is shaded, I include it in my generalized descent set. Let's do a quick example to see how this works. So now I have a maximal chain in this poset, 1, 2, 3, 4. And I've drawn a couple, so I've drawn this chain 3 times, and I've drawn just plus and minus to indicate whether the labeling is increasing or decreasing across that. So the labeling is first decreasing from this edge to this edge, and then it's increasing from this edge to this edge. And I just copied that 3 times. And then I've written down 3 different E sets. So the first is the empty set, and then the set 1, by which I mean this first edge is shaded. And then I've written down 2, 3, which means these second 2 edges are shaded. And then below, we have the descent sets. So in the empty set case, it's just the descent of the usual chain. So it's the position of the minus sign in this picture. In this case, it's a little bit different because we don't pick up a descent anymore from this minus sign, but we do pick up a descent from this 0. And what's happening is that this 0 becomes a descent if and only if the first edge is shaded, and this minus sign is a descent if and only if neither of these edges are shaded, or just the top one is shaded. And then this third one, so I have a 0 here. In this third one, I have the other 2 cases. So unshaded, shaded, I automatically get a generalized descent. And then shaded, shaded, and plus, I get a 1 and a 2. And this is how these generalized descent sets work. This is probably also like the most technical definition in the talk. So the way that I'm going to encode these is with A-B monomials, so monomials and non-commuting variables A and B. Before we saw these things that I was using to keep track of the weights of the chains. Now I'm just going to define some monomials that keep track of my descent sets. So now we're going back to the maximal chain. We have a subset of the edges, and I want to define a monomial which is keeping track of these generalized descents. I'm going to call this thing mon of ME, and it's a product of n things, A's and B's, and I put a B if I is a descent and an A otherwise. So let's go back to our example. Here's the example we just saw, and it's the same maximal chain, and with the same 3 E sets, and we already computed the descent sets, so I just have an ABA here because I have a 1. 0 is not in there, 1 is, and 2 is not. So ABA, here I have BAA because 0 is in and 1 and 2 are not. And then in the third case, 1 and 2 are in my descent set and 0 is not, so I have ABB. Okay. Now we're ready to go back and describe the coefficients of the extended AB index. Did I hear someone cough, or was there a question?
I think it was the elevator.
Ah, okay, great. So let's just remind ourselves this extended AB index, I sum over all chains in my poset minus the 1 hat, and then I take these chain Poincaré polynomials and I stick in a weight of the chain, just this B and A minus B's, keeping track of whether or not something of that rank or the preceding rank was in the chain. And the conjecture of Maglione-Voll said that we have non-negative coefficients. And I want to convince you that their conjecture is true. And in fact, the coefficients of the extended AB index are non-negative for all posets with R-labelings. Here it is. This is the theorem. And I want to explain to you a little bit about what the theorem is saying. This immediately implies Maglione-Voll's conjecture because it's a monomial description. So I just sum over all pairs ME, where M is a maximal chain and E is a subset of its edges. And then I take Y to the number of edges that I've used. So these are the number of edges that I've colored in pink or multiplied by a negative sign or something like this. And then just that descent monomial that we computed a couple times. I want to do an example of computing an extended AB index with this theorem. And then I want to give you a sketch of the proof. So first, we've already seen the extended AB index of this poset on the left. And now I'm going to compute it from the theorem instead of from the definition. And we can see that it's a bit quicker because I'm using this monomial description instead of these weight products. The first thing to notice about what's happening here is that there's two letters in each of these monomials, an A and a B. And the first letter is always an A unless one is in my E set. So first letter is an A in this row, first letter is an A in this row, and in these two rows, 2 and 4, the first letter is a B. So we can focus more on the second letter and what's happening there. So when E is the empty set, Y to the 0 is 1, and I have 3 chains. So I just check what's happening with the increasing, decreasing pattern on each chain, and I record that in my AB monomial. This chain going through A1, this is the maximal chain, which is strictly increasing. So I have an AA. And then the other two, we have these labelings 2, 1 and 3, 1. So both of them have AB and AB. It's an increase and then a decrease. So wait a second. What I want to say is it's something of rank 0, which is not anything, and then it's a decrease. There we go. So I have my AA, which I get here. I have 2 ABs, which are here. And then when I go through the E's, more stuff happens. So let's talk about column by column. This one is increasing, increasing. So I'm just keeping track of, we know what happens in the first letter. And now we're just keeping track of whether or not you had 2 in your E set. And so for these two, there's 2 is not in the E set, and here 2 is in the E set. So I either pick up descent or not. And we can see these more BAs coming in. So BA was from one copy of this thing. Okay. In the second two, basically we have the same thing happening because they're both, while they have 2 different labelings, 2 and 1, 3 and 1, they have the same increasing, decreasing pattern. So they end up getting the same thing. And you can follow the same pattern about, okay, we see that the second letter is a B unless 1 is not in my E set. And then when 1 is in my E set, that B turns into an A. And if you collect these all together, which I don't expect you to have completely internalized at this moment, I'm just taking something in this row, I multiply it by this, something in this row, multiply it by this, and so on, and I get AA plus 3y plus 2y squared, BA plus 2 plus 3y times AB plus y squared BB, which you can trust me, or we can go back together and look and see that it is actually precisely the extended AB index that we computed from the definition earlier in this. So I want to go back to the theorem a little bit, and I want to talk about how this theorem is proved, because I think it uses some cool techniques that surprised me when I saw it for the first time. So remember, I want to give a monomial description of this thing that's defined in terms of weights. And the way that it works is you start with a graded poset and an R labeling lambda. And there's a classical theorem from the theory of R labelings that says the Mobius function can be computed by counting the number of maximal chains on the interval that you want to understand. So we had this example of the poset with a unique top element, unique bottom element, and 3 things in the middle. You could see that we had, let me go back, actually. So this poset, there are 2 chains that are strictly decreasing from 0 to 1, and that corresponds to the fact that the Mobius function value is 2. You can also get the sign by following up with the ranks, but the combinatorics is coming from counting these decreasing chains. And so what you do with the chain Poincaré polynomial is you interpret these products of Mobius function values as like decreasing and increasing maximal chains. So you want to compute a Mobius function value on one of these chains, you like look in that sum and you look at the decreasing part, and then you do the unique increasing part up to the next piece of this interval. And then so you end up with these increasing and decreasing chains. And you use that to reinterpret the Poincaré polynomial. And then you can do inclusion, exclusion on these increasing, decreasing maximal chains to get something non-negative. And by massaging the thing that you get at the top of that inclusion exclusion argument, you end up with these pairs ME. So that's a little bit of an oversimplified outline of the proof, but I think it's a really fun argument. It involves like expanding a product and making choices about how to pull out things in a sum. So it proves the first 2 steps prove the non-negativity part, and the third one gives us this nice monomial presentation that we can like talk about in a talk. Now, for the remainder of the talk, I want to tell you a little bit about the connections to the ordinary AB index and a little bit of connections to things that people have done here.
Your question now. So Galen, I think there's a question.
Oh, yeah.
Yeah, so in that theorem where you're interpreting the Mobius function in terms of decreasing chain, where's the R labeling? Are those like decreasing with respect to R labeling? Or
Yes, sorry. Yes.
So that doesn't depend on.
Sorry?
Yes, it depends on the R labeling.
Well, does the left side?
I can't quite.
No,
He's
the left
asking-
side does not depend upon the R labeling.
Yeah, so he's
Yeah.
asking whether the
But the
right
right
side
side
depends
depends
on the
upon
R
the-
labeling.
But it's invariant.
Yes.
Yeah, but it
Yes,
turns out
yeah.
that the left side doesn't, so it doesn't matter which R labeling. you use, you get the same.
But
So-
I'm not sure if I could hear the question, but I wanted to say the right side, it's decreasing with respect to that R labeling. And this is something really cool about R labelings. For me, this was like, the fact that we could use this theorem to reinterpret the Poincaré polynomial is the reason that we sort of thought R labelings would be the right setting to think about this problem.
Yeah,
Does
so I,
that answer the question?
yeah, I think it's settled. It was the question about
Okay.
the right side depending on R labeling and the left side does not.
Okay.
Okay,
Okay.
super.
Okay. Great. So let's talk about the connections to the ordinary AB index, so not the extended version. So for me, I'm going to define a slight variant of the usual definition of the AB index to be just, I evaluate this extended AB index at y equals 0. So let me show you what I mean. If I take the evaluation of, so I've written now this chart that we did at the very beginning to compute the AB index, the extended AB index, and I've now evaluated everything in this column at 0. And what you'll notice is that the chain Poincaré polynomial evaluated at 0 is always 1. So what I'm really saying is I just keep track of these weights. So what I'm doing here in the empty, for the empty chain, it's 1 times A minus B. And then of course this is 1 times B times A minus B. Here we go. And then this chain just consisting of alpha I is 1 times A minus BB. So here we go. 3 copies of this alpha I, because there's alpha 1, alpha 2, alpha 3. And then there's 3b squared coming from this pair here, this 2-element chain. And so simplifying that down gives me AA plus 2AB. So it's much simpler. But notably, what makes it a little bit different than maybe a usual definition of the AB index is just that I'm using this 0 and 1. So it's like a two length 2 version, maybe. And now I want to define a transformation omega that I'm going to start by defining it on monomials. And it's just a substitution that sends AB, when I see a consecutive pair AB, I send that to AB plus YBA plus YAB plus Y squared BB. And the remaining A's that I haven't switched yet, I want to send to A plus YB, and all remaining B's that haven't been changed yet, I want to send to B plus YA. What I mean is, if I have the monomial AABBA, then omega applied to this monomial should be, okay, I first look at this consecutive pair AB and I replace it with AB plus YBA plus YAB plus Y squared BB. And then I have a remaining A, a B, and an A. So I stick a plus YB in for the A. I stick a B plus YA in for the other B, for the B here, and then the A plus YB for the final A. And I can, of course, multiply these out, but the A and B don't commute with each other, and the Y commutes with everybody. So if you are asking yourself where this lives, maybe think about it living in the polynomial ring Z adjoint Y, but then with the you take like the non-commuting polynomials in AB with coefficients in ZY. I can extend this map by linearity. So instead of applying it just to a monomial, when I have a sum of monomials, I allow myself to apply to the sum individually. And the example here is if I take omega and I apply it to AA plus 2AB, which is that usual AB index that we saw on the previous slide, then I just apply omega to AA, and then, well, there's a 2 out front, so I'll pull the 2 out and just apply omega to AB. And now applying it to AA, I get A plus YB squared. And then I have 2 times AB plus YBA plus YAB plus Y squared BB. And if I simplify that out and rewrite it, so I'm just combining all the Y's together so that I have like descriptions via the AB monomials, I get AA plus 3Y plus 2Y squared BA plus 3Y plus 2AB plus Y squared BB, which you might recognize from earlier in this talk. In fact, it's the extended AB index of this poset that we've been looking at. So we already computed the AB index and it was AA plus 2AB. And we just saw that omega applied to this poset is exactly the extended AB index of this poset. And this is not at all a coincidence. It's true that whenever you have an R-labeled poset, applying omega to the usual AB index recovers for you this extended AB index. So somehow, even if you just know the AB index, the extended AB index is already in there. And I want to, because I'm giving this talk at Kentucky, I feel like I should mention that several specializations have been studied of this omega map have already appeared in the literature. 2 of them from people in this room. So when P is a geometric lattice, the Y equals 1 case recovers the omega map from Billera-Ehrenborg-Readdy. And when P is the lattice of flats of an oriented interval greedoid, setting Y equals to 1, it recovers the omega map of Saliola-Thomas. And when P is a distributive lattice, let me get this right, I think it should be Y equals R plus 1, should recover the omega R map from Ehrenborg related to the signed Birkhoff lattice. And one thing that draws these three special cases together is that they all come from a pair of posets, P, Q, with an order and rank preserving map that sends P to Q, and that the size of the fibers are evaluations of these chain Poincaré polynomials. Now I have to double check and see if there's anything else I wanted to say about this slide. Let's see. Good. I think that's it. I want to give you a short sketch of the proof of this theorem because I think it's a little bit cool how it works. So the theorem is about when you apply this omega map, getting the extended AB index from the regular AB index. And the idea is that you can do this by proving sort of what happens on chains alone. So you fix a maximal chain and you want to show that omega of this chain with respect to the empty set. So you take omega of, oh, okay, here we go. So I want to take just this descent monomial that I used to describe a single maximal chain with respect to the empty set, and I want to apply omega to that and express that in terms of more descent monomials. And by understanding a little bit about how these work and decomposing them into maximal subwords of the form A, B, 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 we get it. So it's just about somehow doing these two reductions. First, you turn it into a sum over all chains and you prove it on the maximal chain level. And second, on all maximal chains, you know a little bit about the structure of these descent monomials. And so you can break it up into a product. And by recombining that product in the right way, you get the result. Cool. So that's a little bit about the proof. That's all I really wanted to tell you guys today about the AB index. So I just wanted to, or the extended AB index. So for now, I'm going to say thank you so much for listening. Here are a couple of references about things that came up in this talk. First, I have this paper about where this omega map we saw for the first time. And then these two papers from Josh and first Lucas Kühne and second Christopher Full. These sort of they lay the groundwork for these extended AB indexes. And then I put Richard Stanley on there so that we can, if you need some references for these R-labelings. Okay. Questions from the audience?
Well, let's thank Galen. We have the clap. Are there any questions?
Wait, I have a question. So,
The question is, can she hear you?
yeah, can you hear me? That's
I can.
good.
You gotta get
I can.
close. Okay.
Thanks. So, because I'm testing this poset transformation, so does the face lattice of the Stump, does that have an R labeling?
That I don't know off the top of my head. So wait, is this thing? I want to find.
If you have the intersection lattice of a hyperplane arrangement, that has a
Yeah.
nice labeling. Is there any
Right.
way, is there any way to extend that R labeling to an R labeling for the face poset of the Stump?
Right.
Because basically, I believe, especially listening up to you here, that the best posets are the posets with R labelings.
Yeah. I mean, I'm convinced that R labelings, posets admitting R labelings are pretty great. And this question about whether or not the face lattice of an oriented matroid admits an R labeling, I thought about this and I thought there was something in this big oriented matroids book about whether or not they're shellable even with a 1 hat, but I don't remember off the top of my head and I don't want to say something that's false. I can send you an email with a longer answer when I look it up again. Somehow I can, well, no.
Yeah.
Yeah, so one thing I was thinking about was the fact that, of course, if you have an AB index, you hope you're in the situation where you can have a CD index, you know, that you do this transformation when you have an Eulerian poset. And I was looking for some kind of symmetry in your coefficients, like this example where you had these three elements of rank 1, and then you had the minimal and maximal element. And I was just looking at the coefficients, you know, like for example, you know, AA has, you know, 1 y to the 0, 0 y to the first, 0 y to the second. Whereas, and so you do have this symmetry, actually, if you look at these coefficients in the y's.
Yes.
Realize that? So I don't know where to go from there, but you have this symmetry happening, you know, like when you had this 3y squared plus, no, 3y plus 2y squared, that sequence of coefficients is 0, 3, 2, whereas 2 plus 3y is 2, 3, 0. So you flip them around. And I don't know if there's any kind of geometry you can get out of this. I mean, that's what I'm always thinking. What's the geometry? I'm looking at Richard saying, what's the geometry, man? So I don't know.
So I will say there is like a symmetry of the coefficients, and it's easier to see on the level of like in the paper we actually describe the coefficients on, like we say, like the coefficient is this set, not described on the monomials. And there's a nice symmetry condition there where you say like the coefficient of y to the blah t, or y to the blah, and then this monomial is equal to this other y to the blah, this monomial, and it's about complements, just that you noticed. There's also this second thing, not geometric, but from this theorem, because of just like the structure of the transformation, you do get something like a CD index, but it's a little odd and I don't know what to do with it. And maybe you guys have a better sense than I do, which is, so usually a CD index, you would expect to have like maybe D or 2D to be this thing, and C to be something like this where you evaluate Y at 1, but now we have like a C1, this would be like my C1 and this would be my C2, which are now polynomials in A, B, and Y. And
Sure.
so
Yeah, so
you
you
get
like
that for free.
you have different variables, different C's, different D's, maybe according to their position. I mean, there are people who've done stuff like that. I just don't remember off the top of my head. I would have to do some scouting around. Okay. Oh, I mean, well, this is super interesting. Any other questions from the audience?
Well, I have another
Oh,
comment.
wait, another comment.
Okay, so Billera together with Stephanie Wilkenberg and one more person, they noticed that Stembridge has this defined peak quasi-symmetric functions, and there he had a map in the quasi-symmetric function world that was actually equivalent to the omega map.
Sorry, one more time. I heard peak enumerators, and
Yeah.
then
Oh, so this is Stembridge with, who is it?
Well, Stembridge had a map.
Oh, Stembridge had the map,
Yeah.
but this was Billera and Van Willigenberg and
Sao or
I want to say Sal.
yeah.
They actually,
They noticed that the omega map was equivalent to the Stembridge map.
yeah, so it's connected with the Stembridge work. They showed that.
right. And I think, so I thought about, okay. So this, I thought about this a little bit and I think that this omega map, it gives you something like a peak enumerator, which is a little bit fun. I mean, it's an A-B statement, but this,
Yeah.
Yeah, sure.
you can reframe the statistic instead of in terms of generalized descents, you can frame it in terms of like,
In terms of peaks.
right, so it's like an A-B pair. So every time you got like a successive A-B, you want to find things that like cover that are, where like, I'm not explaining this well, but like S union S plus 1.
Yeah, well, the AB
Yeah.
is a peak, you know, you're doing an ascent and a descent. So I mean, that makes sense that there should be some peak enumerator in the background and all this stuff. So, okay, great. Any other questions, comments? Cookies? Did anyone else bring cookies besides me? We've never had cookies before, so this is very special. Okay, well, if not, let's thank Galen again.
Thank you guys. Thank you guys for having me, and thanks for like the comments.
Even Caitlin's here. Wow. Hi, Caitlin. She's online. All right. So next week's talk, we're having Gabor Hetchy will be giving a talk, actually online again, even though he'll be visiting in a couple weeks. And to be continued. Thanks again.
Okay,
We
thank
can
you.
go on, but we can let people feel free to leave.
Thanks so much.
Okay.
Around. Thank you so much. We're still going to be here.
Should I stay on the line in case there are other questions? Okay.
Galen, I was just gonna say hello. Hope you're doing well.
Hi.
Go to a
I'm
meeting.
doing well.
Things have worked out for you over there across the ocean. I mean,
Well, you know, it's an adventure and I'm having a lot of fun.
that is
So,
good.
Yeah, I think definitely